Good afternoon, everyone. So I'm Arthur Nishimoto. I am a PhD candidate at the University of Illinois, Chicago, and today I'll be presenting this work that was conducted at the Electronic Visualization Laboratory under the direction of my co-author and advisor, Dr. Andrew Johnson, on using augmented reality to extend virtual reality display wall environments. So the motivation behind this is that large high-resolution display walls are good for collaborative sense-making, where you can have multiple participants in front of these high-resolution display walls enough that you can make out the details when you're standing close to the wall, but then able to step back and get the broader overview. And in these sort of environments, because they are kind of fixed display walls, the field of view and the field of regard is basically restricted by the physical display of the wall without the use of some virtual navigation, such as panning or zooming. But a key feature of having these sort of large display environments is that you get these face-to-face interactions within people, and that they can more naturally interact with each other and help participants have better discussions and make discoveries. In some cases, we have the data that, again, can be displayed above or below the walls. So virtual reality head-mounted displays improve immersion in these environments, particularly when you're exploring three-dimensional spatial data sets. And by filling a single participant's field of view, they can use the head tracking to be able to see more of the virtual environment around them beyond using the user's head rotation, increasing the field of regard so they can look around and see everything. And while the resolution in these headsets are improving with each generation of HMDs, they're still limited compared to high-resolution display walls. And once again, there's a reduced sense of presence, or be able to that sense of yourself in the space. In this case, your collaborators around you, unless you're using some other another medium such as avatars to sort of get around that. Likewise, in augmented reality, particularly in see-through head-mounted displays, you kind of get around the sense of presence and speaking with your collaborators. And you still get the ability to look around with the higher field of regard around the space, but the field of view that you can see at a given time, as well as the resolution, is typically even lower than, say, virtual reality head-mounted displays. And so the main goal of this work is, or the way to combine these technologies together to get the best of both of these environments: the high-resolution display walls, the ability to talk to the people around you, but still able to use a device, an augmented reality device, to regain that sense of immersion, field of regard of the data around you that might not be readily available on just the tile display itself, even if it is at a lower resolution than what's on the display wall. So just a quick look at some of the related work. So the work I'll be focusing on is using these large immersive display walls that tend to do virtual reality work. So, for example, Cave and the LCD successor, Cave 2. And many of these works here provide direct comparisons of the same task on these two different devices. So, for example, the first work, they're exploring a network-based graph, and so they're looking at two participants that are identifying features in these graphs. They're comparing their experience in their Cave 2 versus head-mounted display. But in a lot of these, they have the interaction modalities also different. So in the Cave, they're using wand pointers to interact, whereas in the head-mounted display, they're using leap motion to do more hand gesture work. In the second paper, sort of a similar idea, this time in a projector-based Cave, and they're looking at interacting in these spaces, and again, they're comparing wand navigation to, as the gaze crosshair of this mobile phone-based HMD that was used in here. And so the other area of related works tend to combine augmented reality displays and big displays with the main purpose of using this to simulate outdoor environments to sort of understand how to better improve augmented reality techniques in a controlled environment. So experimenting with interesting factors like how the user perception changes, how the latency particularly changes when you have more fine control because you can use the big display as in a controlled setup. And in both these experiments, these large displays actually are capable of doing 3D stereoscopic graphics, but in this case, since they're perceiving outdoor environments that are far away, they don't necessarily need those cues to depth. And so the work I'm more interested in is when you have a 3D virtual environment, when you have virtual objects that are much closer to the user, and then where those 3D cues of depth are much more important. And so the system that is primarily used for this experiment is the Cave 2 hybrid reality environment we have at the lab. And it's kind of it was designed as a hybrid approach between the high-resolution tile display walls and the immersive classic projection-based caves. And so one of the key features of the environment is that we're surrounding a group of participants with high-resolution stereoscopic visuals that are greater than any VR HMD at the moment. You have this 24-foot space that they can physically walk around to explore the world, as well as large enough to have a group of participants be able to have this face-to-face interaction. And so this was sort of highlighted in the picture above, where we actually had a group of scientists that worked in Cave 2 for a couple of days. They brought in tables. It was basically a working environment where they could actually have, part of the cave with more 2D work that the geologists were more familiar with, so maps, other documents. But then on the right half, or even on the full display when they needed to, have a virtual recreation of this lake bed based on sonar data that they were exploring. In searching for an augmented reality device to sort of add on to this system, the main criteria was that it had to be a see-through display, so again we could preserve the high resolution and be able to keep that sense of presence with the real world, with yourself and your collaborators. And so the main device we worked with is the original HoloLens, since that was the one that was most readily available at the time. But since then, there are certainly other interesting devices that could potentially be used, such as the Magic Leap, which has greater field of view than the HoloLens, as well as also think of other ways that in these kind of collaborative settings, other tools that might be more useful, whether it's having interaction on tablets or maybe more low-cost AR devices that may look at for future work. And so combining these two devices together to get kind of the best of both. So we retrofitted the HoloLens with the retroreflective tracking markers that we used for usual navigation within the cave. And this was done to improve the tracking of the HoloLens as a native tracking system, as well as to kind of minimize the differences as you're trying to compare how this experience would change when we add this head-mounted display with the tracking markers. And so that's pictured in the upper left, where we add the markers, and to preserve the stereoscopic, we actually added the same passive stereo lenses on top. And this is all to give you a general sense of kind of the system. So we have all the inputs are coming to the tracking system, the Cave 2 system, which has the tracking server, and the central master node, which is generating the virtual world and building perspective for all the devices, and then dealing with either feeding that information back to the HoloLens to get the perspectives to line up, as well as going to the computing cluster, which is rendering the displays, the virtual world displays. And so the big experiment here was having this augmented experience would have a significant impact compared to just using this with the standard cave setup of just lightweight glasses and a wand controller. So the experiment that we designed here was an explorative within subject user study, and to evaluate the impact of a spatial search task to this network-based graph, understand how the task performance and the user behavior changed in these two conditions. And so in this case, we had 10 participants for this study, mostly graduate students. Most of them had prior experience with virtual reality, both in the cave or with head-mounted displays. Half of them had some development experience, mostly on the HMD side of things. Half had at least tried HoloLens before, and 3 of them had never used the HoloLens headset. And so the task was a visual search of 3D spatial network graphs. And so it's sort of example of that at the top. That's actually the trainings that they were given. And basically to count the number of triangles formed by exactly 3 nodes in this, one of 32 graph structures that they were presented. And so they were given 16 of these graphs without wearing the HoloLens and 16 with. And these graphs vary in size, node, complexity. But most importantly, they changed on how they were initially presented to the users. So some of them, the graph would be completely viewable on the cave screens to begin with. Some would be on the cave screens that have this extend above. Some would extend below. Some would actually do both. And in most of those cases, since we were very interested in seeing how well the stereoscopic effect would work on having a head-mounted display and in the cave environment, most of these graphs also extended from the projection plane into the cave environment, so they had more of a space that they could walk around the cave and look around the graphs. And in both cases, they still had the option to use the wand controller to do more virtual navigation, so using the control stick to just rotate and move the graph around. And it took about 50 minutes for the users to complete both graphs. So we collected both log data of basically all the tracked movement going on within the cave, the wand button movements, how they were moving the graphs around. And then there were a number of survey data that was collected, so kind of information before the study, and then between after each condition, we did asked a number of questions to assess the physical and mental demand, presence, realism, comfort, sickness, as well as having a short session for just semi-structured interviews to get more interesting feedback from the participants. So the independent variables, we had the control condition was having the participant explore these graphs using the standard Cave 2 glasses as wand, which is pictured in top, so just lightweight 3D passive glasses, same as you would see in the movie theater, using a PlayStation navigation controller with the wand, so they could point and rotate the environment around. And then the experimental condition, instead of wearing the lightweight glasses, they'd have the HoloLens, but they still were able to use the wand controller exactly as they could in the other condition. And then the dependent variables, task accuracy, completion time, as well as several metrics on how they were moving, where they were looking around, both physically and virtually. And so just kind of quick overview of the results. In terms of completion time and accuracy, we didn't find any significant differences between the two conditions, which we did find rather encouraging, since one of the biggest criticisms of wearing the HoloLens was the discomfort, and even with the kind of limited field of view. And since this was for the kind of the first iteration of this system, there was a decent latency between when the participant would move their head and the graphics lining up, which is around 375 milliseconds, and there was a bit of a range in there depending on various conditions that we're hoping to improve in future work. In terms of movement, we noticed that participants that had the HoloLens on would use the wand to virtually navigate significantly less in the data set compared to using the Cave 2 condition. So they were able to looking around more versus flying around. And this sort of is connected with some of the interview responses, is that when they had the HoloLens on, it was easier for them to maintain spatial awareness and not have to move back and forth to get a better sense, did I count this section of the graph again, or do I have to recount all the nodes? In terms of the survey responses we got, in terms of mental, the only significance we found was that the HoloLens was more uncomfortable than wearing the glasses. Physical and mental demand we didn't find any significance for that. And wearing the HoloLens did not significantly impact the sense of presence in the Cave 2, which was also kind of nice to see, given that wearing the HoloLens, it does change the contrast as you're wearing it, as well as there is some limitations to the field of view compared to the other just wearing the glasses. Just quickly, just some of the interesting interview responses is that I've already mentioned it was easier to count in the HoloLens. One of the more interesting notions is in the K2 displays, it's these large tiled displays and it has display borders, and most people find that distracting at first. Usually they adjust as they get used to the environment. But in terms of the search task, the grid actually became more useful again in terms of partitioning the spaces, and actually became more distracting with the HoloLens, which is just a flat display and didn't have that grid. It's like, oh, the grid is gone, and they found it distracting, which I thought was an interesting, just perceptual response. So just recap, this is sort of preliminary work in combining these large VR display walls and augmented reality, trying to get the best of both of these devices. And so we developed this framework that fairly reliably was able to get these pieces working together without a significant user impact. And so future work would be to kind of explore this even further as part of my PhD dissertation, and use this with more complex data sets and examine multi-user interaction within this framework. Thank you.
Thank you. Question?
Hi, Wells, Virginia Tech. Do you think you saw any effect due to the fact that the HoloLens is kind of heavier than the glasses that you use in the control condition? Did any participant tell anything like, oh, I avoided looking up and down too much because the thing is heavy on my head?
Yeah. So in addition to the comfort, we did, a number of participants noticed that they said they were less inclined to look up and down, particularly in the graphs, because of the heaviness because of the weight of the headset. Although I believe there was still a significant portion of at least they tried, even though they said some of the participants said they didn't even like the HoloLens at all in the condition, but overall even they still at least made attempts to look up and particularly down. And something that I think I want to explore also later is whether there was a difference in if they're looking up versus looking down. So again, since the weight differential could be also interesting.
Any other question? So you basically compared cave only and cave plus HMD. Mm-hmm. So how about HMD only condition?
Right, no, absolutely. That is something I want to explore in future work to get a better sense of how these would compare again, and would be a better comparison to some of the prior work that were specifically looking at the interactions. But yes, again, this was the first step of seeing where we can go with this combined AR display. But I think, future work, particularly for my dissertation, I do intend to explore a HMD-only case as well.
Other question?